Hello, this is Team 3 Process Improvement Plan for the Tesla electronic vehicle battery production. Team 3 is Abir Kamal, Dua Idris, Imri, Ibtisam Al-Ghamdi, and Tomislav. This plan addresses the challenges of Tesla's battery production hell. We'll balance automation with human expertise for optimal efficiency. Our process-driven approach will enhance sustainability while boosting electronic vehicle battery production capacity. Let's transform Tesla's EV battery production for the future. So for our project, we selected Tesla, and we chose to focus specifically on their battery production process. Now, most people know Tesla as a leader in electronic vehicles. But Tesla's operations are much broader than just car manufacturing. They're vertically integrated, which means they handle everything from design to battery production to software and even energy storage solutions. We chose to focus on the battery production for a few reasons. First, it's at the core of Tesla's value proposition. The battery determines how far the car can go, how quickly it charges, and even how much it costs. It's not just another part, it's the engine of the EV era. Secondly, battery production is where Tesla invests heavily. Think about their gigafactories in Nevada, Texas, Germany, and Shanghai. These factories are designed for massive output, but with that scale comes complexity. And that's where operational efficiency becomes critical. Also, Tesla has been innovating aggressively with new battery formats like their 4680 cell, and trying to move more of the production in-house to reduce reliance on suppliers. But even with all this innovation, there are still process bottlenecks and quality issues, especially with the newer battery formats. So for us, battery production felt like the right place to zoom in, because improving this one process could have a ripple effect across cost, delivery time, and sustainability performance. It's where both risk and opportunity are concentrated. Now, in terms of why this process needs improvement right now, we looked at the major market disruptions impacting Tesla, and honestly, it's a perfect storm. One of the biggest issues is raw material availability. Lithium, cobalt, and nickel are essential for making EV batteries, but they're hard to get. Prices are rising, and many of the sources are in politically unstable or environmentally sensitive regions. This creates a huge risk for supply continuity and cost. And then you have geopolitical peace with tensions across between the US and China. We're seeing more restrictions on exports and critical minerals. And countries like Indonesia are starting to limit exports to push for domestic processing. This adds complexity to Tesla's global sourcing strategy. On top of all that, there is inflation. Energy prices, labor costs, transportation, they've all gone up. And that directly impacts the cost per kilowatt hour of a battery. Even though Tesla has scale, they're still vulnerable to these micro shifts. And let's not forget the competition, especially from China. BYD, the Chinese brand, for example, is scaling fast and catching up on innovation. That adds pressure for Tesla to streamline its operation and stay ahead. All of these disruptions point to a need for process improvements in battery production. Whether it's increasing automation, reducing defects, diversifying suppliers, or improving energy efficiencies, the goal is to make the process more resilient, more cost-effective, and better aligned with sustainability expectations. That's why we're here, looking at how Tesla can evolve its battery production to navigate today's challenges and stay competitive in the long run. Now, let's look at Tesla's battery production process, which is the heart of the company's innovation and operational challenge. The process starts with material preparation, where raw materials like lithium, nickel, and cobalt are ethically sourced and go through inspection and pre-treatment. Next is cell assembly. This includes electrode mixing, coating, drying, and assembling Tesla's 4680 cells. These are designed to increase energy density and reduce manufacturing steps. Then we have formation and quality control. Here, the battery cells are charged and aged to stabilize performance. This phase also includes intensive safety, thermal, and electrical testing. Finally, in module and pack assembly, the cells are grouped into modules and integrated into battery packs using the GigaPress for structural casting. Each pack undergoes final performance certification before deployment. Despite Tesla's technological leadership, this process faces two major challenges. One, high production costs, and two, raw material constraints. Our improvement plan focusing on solving exactly that. Here we are presenting a detailed breakdown of defective areas identified across Tesla's battery production workflow and how they relate to the 7 lean waste types. Starting with material preparation, we see that delays during raw material inspection and inconsistencies in lithium or cobalt purity leads to both weighting and defects. These input issues can cascade through the rest of the production process. In the cell assembly stage, one of the most critical pain points is uneven electrode coating and alignment problem during the 4680 tab-less cell build. These defects drive over-processing, as extra checks or rework is needed, and ultimately increases scrap. The formation and quality control phase is another bottleneck. Long idle times during the aging cycle and high rejection rates at this stage lead to excessive waiting, inventory buildup, and further defects. This not only is inefficient, but energy intensive as well. Lastly, in the module and pack assembly, errors from the GigaPress casting process and post-assembly inspection rework contribute to motion waste, defects, and overprocessing. Each of these problem areas present an opportunity, and our proposed improvement target these pain points directly through layout optimization, automation balancing, and real-time analytics, as you'll see in the revised process later on. Using lean principles, we identified 7 key types of waste in Tesla's battery production process, commonly known by the acronym of TIMWOOD. First is transportation. Materials often move unnecessarily between processes like GigaPress and final inspection. Inventory is another concern. Aging, work in progress, and surplus raw material stock can slow down throughput. Motion waste occurs due to inefficient equipment layout that forces staff to travel between stations. Waiting is significant during formation cycles where cell sits idle during the aging or the pre-quality control holds periods. We also see overproduction, cells produced without real-time demand forecasting leading to waste. Overprocessing arises when manual inspections duplicate AI-based quality checks. And finally, defects, such as micro cracks in electrodes or misalignments during cell assembly, which lead to rework and waste. These inefficiencies represent major cost and sustainability risks. Addressing them is the core of our proposed process redesign. This revised process mapping is designed to eliminate inefficiencies while strengthening quality control. We've added early-stage material validation, automated inline defect detection, and real-time testing to reduce delays and rework. Using innovative technologies such as AI and blockchain, and the revised process has improved equipment layout to minimize waste, and with the blockchain integration for enhancing supply chain, and the overall support of AI for both quality and focusing on minimizing waste and minimizing the reuse, repair, refurbishment, and recycling of products and materials to create a closed-loop system. This new system directly tackles the 7 types of lean waste. We've reduced waiting time by automating inspections and allowing multiple checks to run in parallel. Transportation has been minimized by restructuring our inspection points closer to the production line. Overproduction is avoided through just-in-time testing and demand-driven scheduling. Defects are identified early, limiting rework and scrap. Overprocessing is cut down by replacing redundant manual tasks with AI-based sensors. Inventory is kept lean with controlled batch sizes, and unnecessary motion is reduced through better equipment layout and robotics. This upgrade improves efficiency, lowers costs, and delivers higher quality battery packs on time to vehicle assembly, all aligned with Tesla's mission of innovation and operational excellence. The impact we are hoping to achieve for proposing the revised process map is balance automation, data-driven operation, and streamline workflows and supply chain integration by embedding technologies like AI, advanced analytics, and blockchain. Now, with the improvements we are suggesting, the risk management framework also needs optimization. Operational risks like machine downtime and yield issues should be addressed through predictive maintenance powered by AI and by building buffer capacity where it matters most. Market and geopolitical risks should be mitigated by localizing critical suppliers and using blockchain for transparent tracking, so they have more visibility to the delays or the vulnerabilities anticipated. Regulatory and compliance risks will be built into the digital dashboard, integrating emissions, safety, and ethical sourcing into the same view that is used to manage production. In summary, Tesla would move from reacting to proactive risk management framework. Our improvements proposed aren't just about the end results, but also they're about the ESG responsibility. Environmentally, we're shifting from passive recycling to an active circular economy model. We propose introducing real-time scrap tracking, integrated material recovery lines, and design for cycling practices. For example, restructuring cell packaging to enable 80% plus reuse of key materials like nickel and lithium. Socially, we're taking a deeper look at the human side of battery production. Our plan includes implementing sensor-based ergonomic monitoring, expanding cross-training programs to reduce repetitive efforts, and using team feedback to refine workstation design. The Kaizen logic. This reduces injury risk, and improves morale and retention. Governance means accountability. Today, ESG metrics are often siloed. We propose integrating ESG KPIs directly into our digital production dashboards, visible to line leaders, not only just executives. With these changes, ESG isn't a separate initiative, it becomes integrated within Tesla's operations. In order to measure and track the efficiency of the revised process, KPIs come in place across people, planet, and profit. And this is to ensure successful implementation. Under people, we're looking for 100% ethical sourcing verification. Every part of production process that includes any Tesla employee must meet Tesla's environmental and social values. We're targeting 30% reduction in workplace incidents through ergonomic redesign and smarter layouts. We're targeting 85% employee retention, keeping skilled resources by making Tesla a better place to work. For the planet, the target is 50% cut in emissions per battery by improving energy efficiencies and smarter sourcing, 90% water recycling, especially critical in dry region gigafactories, and 80% material recovery, moving from recycling to full resource recovery. Profit, the target is 25% production cost reduction through fewer defects, less rework, optimized equipment layouts, 20% increase in throughput, better flow, which equals more batteries and faster, 15% reduction in warranty claims. These KPIs aren't abstract metrics. They're the proof of progress. Every team, every shift, every improvement should lead with these numbers. Thank you so much for your kind patience. Thank you so much for listening to us. We hope that we have done a great job in our presentation.